turbulent and lively. Okay. And after the gas is accreted, is processed to form new stars. It can be ejected and eventually reaccreted back on the galaxy. But what I'm particularly interested in is this on even smaller scale. Okay, sorry. This little guy sitting at the center of galaxies, this is a supermassive black hole, which accretes gas and dust from the surrounding. And during this process, it produces a huge amount of energy, which is much larger than the galaxy binding energy. So supermassive black holes in this situation are called active galactic nuclei, or AGN from now on. And so if we consider that even a small amount of this energy could couple to the interstellar medium in the galaxy, we may expect some effects of the AGN on the further evolution of the galaxy. And now if we take a step back and we look at the galaxy population as a whole, we realize that there is some indirect evidence towards the connection between supermassive black holes and their host galaxies. For example, we observe this correlation between the mass of the galaxy and the mass of the supermassive black hole, which I find quite remarkable and fascinating if we consider the supermassive black holes and galaxies differ in physical scale by several orders of magnitude, but still it looks like they know about each other. And then if we consider the growth history of galaxies through the star formation rate in yellow and the accretion rate of supermassive black hole in blue, we see that they have a very similar trend. And in particular, there is a peak in their growth histories when the universe was 3-4 giga-years old. And this is quite a key cosmic epoch in the universe, is the so-called cosmic noon, because we observe the peak in these trends, and it's when the energy injected by the supermassive black hole into the host galaxy is maximized. And this is what we are going to focus later on in the talk. So the collection of mechanisms through which the AGN can regulate the growth of the host galaxy is the so-called AGN feedback. And one of the, let's say, flavors of AGN feedback that researchers are focusing on is outflows. So these gaseous winds that are actually a big multi-scale and multi-phase challenge, especially from an observational point of view. So winds are launched from the accretion disk surrounding the supermassive black hole, and we can observe them in the X-ray through highly ionized disk winds. Then further into the host galaxy on parsec, kiloparsec scale, we observe, for example, in the submillimeter and radio cold molecular gas winds, which are usually identified through these broad and often blue shifted components in the emission line. And then on tens of kiloparsec scale, we can observe winds in the optical and near infrared, especially in the ionized phase. And we see here this very nice example of a local galaxy with the galaxy disk in red, traced by H alpha. And then in oxygen 3, here in the map is in green, we see this biconical structure that is produced by the outflow. So the bottom message here is that outflows are ubiquitous in the universe. They've been observed at different redshifts in different types of galaxies. But what we miss now is the kind of conclusive evidence that they are able to regulate star formation in the host galaxy. Okay, so since I'm an observer, let's look at possible ways to find these effects of AGN feedback. And on the one hand, we can characterize the feedback mechanism itself, so measure outflow properties. And on the other hand, we can study the properties of the galaxy that are impacted by feedback, and in particular, the star formation activity and the cold gas content. And here I refer to the cold gas because it's the direct fuel for future star formation. And in terms of tracers, we can consider, for example, tracers of ionized gas, such as the oxygen 3 line and carbon 4. And for the star formation activity, we can, for example, look at the far-infrared emission of the galaxy, which is produced by dust heated by star formation. And as for the molecular gas, one of the most popular tracers is the carbon monoxide molecule, which emits in the submillimeter regime. So consider this as a sort of recipe with the ingredients that we'll see in the rest of the presentation. But before moving on, I wanted to spend a few words on why oxygen-3 is such a popular tracer. So it's a bright line tracing ionized gas, and it's forbidden, therefore it requires low densities to be produced. And these densities are it can be found in the narrow line region here in blue. So basically parsec to kiloparsec scale distance from the supermassive black hole. And therefore, this gas is not subject to the fast gravitationally bound motion, which are instead typical of the broadline region here in red, so subparsec scale from the supermassive black hole. And this is the reason why, as you see here in the blue box, broad and quite often blue shifted emission in the line has been associated to non-circular motions and quite often to outflows. And then the other important point here is that in the last few decades, we have gained quite precious information on outflows thanks to integral field spectroscopy observations. And indeed, with integral field spectroscopy on top of the wavelength information, we also add the spatial information. And this means that we can, for example, integrate the emission in the blue box, so tracing this blue shifted and broad component, and we can map the distribution of the outflow in the galaxy. Okay, this is kind of projected into D, but you see here in white the outflow. And if we have a tracer of star formation, so here in red, we can also see, it's been observed in a few of particular cases where there is an anti-correlation between the distribution of the outflow and star formation. So meaning that the outflow is somehow affecting instantaneously the star formation rate. But in general, we need this kind of data to obtain details on the extension and the morphology of outflows. And this is also the technique that we'll see later on. So what's the kind of integral field spectroscopy landscape that we have obtained? In this plot, you see the AGN luminosity as a function of redshift for targets with observations of outflows in oxygen-3 using integral field spectroscopy. And you can notice here that in the local universe, the coverage in AGN luminosity is quite uniform. But then when we move to higher redshift, so higher than 1, if we focus on the black data points, then we see that the observations are quite biased, meaning that they target very bright objects, or for example, like AGN with known strong outflows. And a cosmic noon, so around redshift 2, there are two complementary surveys that are trying to address this bias. One in red is SUPER, which I'm going to talk about in a moment, which covers a wide range in AGN luminosity, high resolution observations. So of course the statistics is quite limited. And the other survey in blue, CASH-Z, using KMOS, covers a wider redshift range, a much larger statistical sample, but also lower resolution observations. So some details about SUPER. This started as a large program with SINFONI, an instrument that was mounted on the Very Large Telescope in Paranal, and using adaptive optics. So this is why we could achieve higher resolution. It's designed as a blind survey, so we didn't preselect for the presence of outflows in our targets. It was just a selection of 30 AGN based on an X-ray, with their X-ray emission. And we try to get targets from the deepest fields of the sky. If you're familiar with them, they're related here, like Cosmos and CTFS, for example. And if you want some more details on the multivalent characterization of the sample, you can check our survey paper from 2018. And in terms of observations, we covered in in H-band the oxygen-3 line, and in K-band the H-alpha line, which can be a possible tracer for star formation. As for the resolution, so this is the same plots that you saw earlier in the previous slide, but in this case on the y-axis we have the spatial resolution of these observations, and you can see that in red here we could achieve the highest resolution that were available when we proposed the survey, so around 2 kiloparsec. Okay, so now let's see how what we learned in the characterization of ionized outflows. For this work, it's a combination of data. So we could join the SINFONI observations, of course, with also publicly available SDSS spectra tracing the carbon-4 line. And in this way, we could probe outflows from parsec to kiloparsec scales. So as I said earlier, oxygen-3 is produced in the narrow-line region, while carbon-4 is produced in the broad-line region, so closer to the supermassive black hole. And you see here an example of a SINFONI spectrum with the 2 oxygen-3 line and H beta and the outflow map. So this is the velocity of the outflow and the width of the line. And you see, for example, the fastest velocity of the outflows correspond also to the kind of widest, like the broadest width. So what did we learn? We detected outflows in all the targets analyzed, and this is analysis carried out on the sample made of unobscured AGN type 1, where we could see, let's say, directly close to the supermassive black hole. The outflow was partially resolved for 35% of the sample, with outflows extended up to 6 kiloparsec in physical scale. We found also a correlation between the velocity of the outflows in the narrow line region and in the broad line region, meaning that the kind of outflows on smaller physical scale can affect the kinematics on larger physical scales. We also found that more powerful AGN, you see here on the x-axis, the AGN luminosity, drive faster and also more massive outflows. You see here this scaling relation of the mass outflow rate as a function of AGN luminosity. So now that we have, let's say, characterized our outflows, we want to understand their impact on the star formation activity in the galaxy. And here I call this the dusty view because we used dust continuum emission as a proxy for star formation rate. And in particular, this work was led by Isabella Lamperti. We obtain ALMA observations for a subsample of the super targets that we saw earlier, with the same resolution as what we had from SINFONI. So you can see 2 examples here where in the foreground in white, we see the dust distribution for these 2 objects. And in the background, there is the map of the outflow, the oxygen-3 outflow, obtained by collapsing the blue channels in the spectrum. And what we found out for these targets is that there was no clear anti-correlation between the outflow, the distribution of the outflow and star formation. So basically, where the dust is the outflow is distributed, there is also star formation. So what we concluded here is that there was no, we couldn't find any instantaneous impact of the outflow on star formation. But this doesn't mean that nothing is happening, because we need to consider a few aspects. So first of all, for example, it could be that this impact is happening on smaller physical scales than what we are probing with our couple of kiloparsec resolution. Or it could be that the outflow needs more time, it needs longer time scale to have an effect on star formation. And the other point is that the time scale for outflow is quite quick, a few 10 mega a year, while the time scale we are probing with the star formation rate tracer is around 100 mega a year. So there could also be a mismatch between the time scales that we are probing. So yeah, probing this kind of effect with the direct tracer of star formation rates, such as the dust continuum, is quite difficult. So what can we do next? We can turn our attention to the cold gas reservoir, because any effects from the AGN will have an impact on the gas reservoir first, and then on star formation as a consequence. And so if we start with the idea that AGN feedback may play a role in affecting the gas reservoir of the host galaxies, then we can ask ourselves this question. So do AGN show a different gas content if we compare them with a control sample of inactive or non-AGN galaxies? So if we look at the literature, the answer in the local universe is no. Works analyze different tracers, but then this is an example by Usman and collaborators where they show the integrated Schmidt-Kennicutt relation. So star formation rate is a function of molecular gas mass. And they found that AGN and inactive galaxies occupy the same area of the parameter space. But then if we go to high redshift, like higher than 1, the answer is a bit more difficult. It is not the same for all the studies. But many works showed that AGN are sort of displaced in this parameter space with respect to inactive galaxies. And for a given star formation rate or far infrared luminosity, they show lower CO emission. However, the difficulty at high redshift is due to the fact that these works are either focused on a few often bright targets, or to have more statistics, of course, they assemble literature samples. And this means that we are putting together more transitions of the CO molecule. So what you see here is the CO ladder. And therefore, to have everything on a kind of comparable ground, we need to assume uncertain and unknown excitation factors in order to get quite often the ground 1 to 0 transition. And this, of course, injects further biases in our analysis. So this is what we try to address with the ALMA follow-up of the super sample. So we obtained ALMA observations in band 3 of the CO 322 line. The observations are integrated around 1 arc second of spatial resolution, angular resolution, sorry. And you see an example here of a map and the flux map and the spectrum. This represents the first systematic study of the molecular gas content of AGN at this redshift with the goal of minimizing assumptions on conversion factors. And so now that we have our AGN sample, we can assemble our control sample of inactive galaxies that we took from the literature, and we matched these galaxies in redshift, stellar mass, star formation rate. And the most important point is that we took galaxies observed in the same CO transition as our AGN in order to avoid all the conversion factors needed that I was mentioning in the previous slide. And in this plot here, you see the distribution of the targets, the two populations, on the main sequence of star-forming galaxies. So star formation rates as a function of stellar mass. We try to ensure that the two samples were occupying the same parameter space. And in terms of AGN luminosity, we cover a range of about 2 orders of magnitude. So trying also to probe the less luminous, if you want, AGN, although the luminosities are quite high. And before showing you some results, I wanted to also describe another work that we are now completing, led by Elena Bertola, a postdoc in Florence. So the issue we wanted to address is clear from this plot. So you see super still cover quite a high bolometric luminosity. So what Elena did was to complement this sample with CASH-Z, the survey mentioned earlier. So still a survey to probe AGN outflows with CAMOS. And CASH-Z also goes, well, covers first of all a larger redshift range, but also goes a bit lower in terms of AGN luminosities. So Elena mined the ALMA archive in order to search for CO observations of these targets, and assembled a sample of around 40 AGN with observations of 2 CO lines, so 2 to 1 and 3 to 2. A bit more heterogeneous in terms of resolution and redshift and emission line covered. But the idea was to build an archival study of the molecular gas content of AGN by also increasing the amount of lower luminosity or more regular AGN, if you want. But all the rest was maintained consistent with what we did for the other sample. Okay, so now I'm going to show you how the CO content of AGN compared to the content of inactive galaxies for a given star formation rate and as a function of stellar mass. So we are going to see also the distribution of the gas fractions, which is the molecular gas mass divided by per unit stellar mass. And I will use the CO luminosity as a proxy for the molecular gas content, and the far-infrared luminosity as a proxy for the star formation rate. So what we found by focusing on the super sample is that AGN, you see them in red, show lower CO luminosities for given star formation rate, and also in the distribution of the gas fractions, they are displayed at lower values. So what you may notice if you see all the little arrows is that we have a lot of upper limits, unfortunately, in the survey. And so to tackle them as best as to include them in the analysis as best as possible, we implemented a Bayesian statistical framework. I won't go into the details, but if you have questions, we can talk about it later. But what we found is that the result is significant at the 2-3 sigma level. And then implementing, complementing the analysis with also the Kashi sample, we found similar results, both as a function of star formation rate and for the gas fraction. So we struggled a bit because the result, here the significance is still mild. But yeah, we found basically consistent results in the two cases. And so we ascribe, first of all, I wanted to draw your attention to again, to the distribution of gas fractions and make a comparison with an interesting comparison with the local universe. So this is a result, the one on the right, that was published a couple of years ago for a sample of local Seyferts. And well, the color coding is the same, so I think the similarity is quite clear. The difference is that in these local galaxies, they could disentangle the area of the galaxy that was dominated by AGN activity, and the area of the galaxy was dominated by star formation activity. And what they found is that let's say the pixel dominated by the AGN all show consistently lower gas fraction compared to the blue distributions. And so I told you earlier that there is no difference in the local universe, but actually with gaining more information on the central area of the galaxies, for example, we start to see some differences. So it's quite interesting and promising for the future. But overall, we ascribe these effects to the activity of the AGN. And for example, the CO emission could be heated, dissociated, excited by the strong AGN radiation field. And here I show you an interesting example in the local universe of a Seifert galaxy published by Rosario and collaborators, where they could observe the CO emission in yellow and orange. And what they found is that there is a lacuna, a depletion of CO emission around the central engine, or 100 of parsec scale. However, this CO lacuna is filled with warm molecular and ionized gas. So it's like the gas is there, it's just in a hotter status and not able to form stars. And this could be similar to what may be happening in our objects. It's just that the AGN is more powerful, and therefore it could be extended of kiloparsec scale, for example. And this is why in our integrated observations we see lower CO emission. It could also be the AGN-driven outflows are affecting the gas reservoir, and this was also the let's say the scenario proposed for a few bright AGN at high redshift. So in the last part of the talk, I would like to talk about something different but complementary to what I showed you so far. So I said at the beginning that we need interval field spectroscopy observations to obtain detailed studies and learn about the physics of AGN feedback. However, especially at high redshift, this kind of technique is still lacking statistics, and therefore we are not able to perform studies over very large AGN populations and obtain scaling relations, for example, telling us how the outflow properties vary as a function of galaxy and AGN properties. But it's something we can still do with spectroscopic surveys. And for example, so far we learned many interesting things. For example, that outflows are more prevalent in AGN than in non-AGN or inactive galaxies. And you see here the clear difference in the oxygen tree-line profile for star-forming galaxies and type 1 AGN with this broad and blue shifted component. And we also saw the more powerful AGN, you see here the trend with AGN luminosity, develop more powerful outflows, as traced here by the fluidal maximum of the line. But this result, mainly obtained with SDSS, can get to redshift of 0.4. However, ideally, we'd like to go even more back in time and up to at least cosmic noon, where we saw there is the peak in the activity of supermassive black holes. And this is something that we can do with the dark energy spectroscopic instruments, or DESI. This is actually a cosmological survey to obtain information on dark energy, which over the next few years will obtain redshift for 40 million objects. And in particular, we expect to obtain redshift for and spectra for 3 million AGN. And the idea here is to use DESI to study the physics of galaxies and AGN, and in particular obtain, as you can see in this scheme, like a large sample of targets, probe the oxygen tree line to check any broad components and trace outflows, and then obtain outflow scaling relations that then can be used to test models of galaxy evolution. And in particular, we can, considering the wavelength coverage, we can probe the oxygen tree line up to redshift 1. And we can study, we can determine, for example, the occurrence of outflows, and in this way bridge the gap between what we can do in the local universe with SDSS and other surveys that in the future will be focused on cosmic noon, for example, at the VLT or the Super-O telescopes. And then just some quick details about DESI. It's an optical multi-fiber instrument installed at the Mayal telescope at Kitt Peak in the USA. Here in the picture, you can see the focal plane and the telescope. So it has 5,000 fibers, 10 spectrographs, and a wavelength coverage between 3,600 and 9,800 angstrom. The resolution is up to a factor of 2 better than SDSS. And in terms of targets observed, so DESI has different target classes like bright galaxies, emission line galaxies, quasars, and so on, in order to probe different populations at different redshifts. And you can see here distribution of the redshifts for the survey validation observations that we obtained. So we have, of course, a clear target class made of quasars, which were selected to be compact in imaging, but then we can still identify many AGN also in the other target classes that were instead focusing on galaxies in general. For example, by using optical emission line, X-ray emission, and so on. So work that is ongoing in the collaboration is to build a large AGN catalog that is collecting all the AGN from all the target classes that are available. And so what, to show you some results of what we are finalizing. So we are taking the AGN catalog. So in this case, it's 70,000 AGN. We fit the oxygen tree line. We try to fit with 1 and 2 Gaussian components to see if there is any evidence for a broad second component needed to fit best the line. And we find that this is necessary in 15% of our sources. You see here the redshift distribution of the sample, and in those cases where we need a second broad component, the flux in this component is peaks at around 50% with respect to the total flux of the line. And one way we can start to check whether there is any evidence of outflow and like blue shifted emission is to look at the velocity shift between the narrow and the broad Gaussian components. As you can see here, the distribution is a function of redshift. And you see that the distribution is like mainly offset towards negative velocity shifts. And in particular, this shift is increasing towards higher redshift. And another kind of trend we can look at, for example, is again for this velocity shift and its evolution as a function of AGN luminosity. And you see here again that we found this trend of more negative velocity shifts for higher AGN luminosities. So this is something that has been observed as well in the local universe, but I think it's quite promising to see these results going up to redshift 1. Yes, so this brings me to my summary. So I hope I showed you that a multivalent approach is crucial to gain further information on the role of AGN in galaxy evolution. From the ionized view of outflows, we saw that they are ubiquitous in AGN at cosmic noon, and we need interface spectroscopy data to constrain, best the properties of the outflows. However, to gain knowledge on statistical populations of AGN, we can exploit results from spectroscopic surveys. And from the dusty view, we saw that the impact of outflows on star formation is elusive, quite difficult to constrain. And then if we turn our attention to the molecular view, we found the AGN show lower CO content with respect to inactive galaxies, but we have, the significance is not very strong, especially when including a lower luminosity AGN. But we interpret this as a hint towards the effect of AGN activity. Thank you very much for your attention. That's it.
Thank you so much for the talk. We have now time for questions or comments. Okay, great.
I have a few questions, but I would like to do at least two. Okay, one is a comment more than a question. The first one is when you were looking for the feedback, AGN feedback on star formation, no?
Mm-hmm.
You mentioned different proxies there, but I wonder, what do you think about the geometry of the system? No, it's not the same if the outflow is in the direction of the galaxy disk or is perpendicular to that.
Yes, well, that's a very good point. But so indeed, in the maps I showed, is like 2D projected emission. So we couldn't track the geometry of the outflow. In this case, you need to do 3D modeling, which I think is quite difficult at this high redshift. So it's being done in the local universe for targets where you have, of course, better details. But in this case, we just got the projected emission. So yeah, this is another point, because you don't know whether like the direction of the outflow is taking.
So the new generation of large telescope will help you to to prove the geometry of these systems. Okay.
Yes.
And my second question is a curiosity. One of the last plots you showed there with the distribution, that one, no, the green one, with the distribution of the AGN with redshift.
Yes.
Is a bimodal?
So yes, so in this case, it's an effect due to the selection techniques that we used to get the AGN. So this first peak is due to the fact that we used BPT diagrams to, the ratios between optical emission lines. And in the BPT diagram, there is H alpha. So H alpha kind of gets out of the covered wavelength range at redshift 0.5. So basically, we have a kind of a peak here because it's the BPT diagram selection. And the other peak here is due to the specific quasar target class, because as you see in this slide, so the quasar target class is not peaking at this up to redshift 1, but is peaking at higher redshift. So that's dominating in the other part of the distribution.
Yes, I expect something like that, no, like increasing from the nearby to the.
Yes.
And I missed what is
basically what you're getting here is the galaxies selected to be AGN from the BPT diagram. Yeah.
Okay, thank you.
More questions?
Yeah, thank you for the talk. Very nice. So, for example, regarding Ian Scholl's result on the no clear anticorrelation between
Yes.
star formation and outflow, the star formation is traced by with the dust,
Yes.
and the outflow H alpha,
Oxygen 3.
oxygen 3. Okay, because I was thinking in contamination, but
Yeah, well, we also compared with the H alpha that will go
Darsham.
from K band. But in some of the cases, we found H alpha is contaminated by the agent itself, so it's not very reliable as a star formation rate tracers. In another case, it's not clearly contaminated. In some cases, we could identify the ionization source. So yeah, it's a bit of a mix. It's a risky, let's say, tracer to use. But we found with H alpha for those cases where we could see that it was driven by star formation, there was a hint of anti-correlation again, also in the super sample. But it's kind of a tricky tracer to use. Yes.
And if I may, or yeah, okay. And in the comparison between super and FIPS, when you look at the CO,
Yes.
so I know that you did a lot of statistical tests to see if there is a difference between the two, no? I mean,
Yep.
because you have a lot of upper limits, but it's funny that for the sources where you have the detections, which are not many in the case of the AGN, the range of CO masses that you are covering is the same more or less, right, as the FIBS. Like if you take only the detections, I mean, you find massive as large as in the control sample, no? So yeah, I don't know. I mean,
but that's like I guess it's also due to the flux limit that you reach with ALMA, and this was also, since we got all these upper limits, it meant that the estimates we did at the beginning to observe like for the integration time of these targets were calibrated on the classic far infrared CO correlations. And so the fact that we didn't observe them means that their CO flux is below our detection limit. So this is why we wanted to include them as much as possible, because probably these upper limits are also telling you something.
Of course, no doubt about that. No, but in the most optimistic scenario that your upper limits were all like, if you would have detected, it would be only like a little bit lower, which is very unlikely. Would they be similar? I mean, I don't know. Still, I think the FIBS would be a bit more massive.
Yeah, probably. Yeah. Well, I didn't do like the test just by assuming that the non-detections were detections. Probably quite more similar than what we see. Yeah, I guess so.
Thanks, Chiara, for this very nice talk. Very interesting results. I wonder, you mentioned that the SINFONI observations were in AO, so you could resolve the outflows. And on average, they have like 6 kiloparsecs chaos.
For those, yeah, it's like a 30%.
So could you resolve in the images, like if they had like a preferential direction, like, and if these outflows, if they reach this large scales, are they able to escape the galaxy potential, or they will probably run back to the galaxy?
Yeah. So in terms of the geometry, I mean, we could just say, for example, if you see a clear displacement, like the area with the highest velocities on a side, you say, okay, well, maybe that's the direction of the outflow.
But do you see like biconical outflows, or
no,
one
it's
direction,
in
or
most cases
outflows?
like a roundish shape. Yeah, no, I think that the geometry part is quite difficult. In some cases, yeah, you can see more like a hint of a biconical structure, but I think it's quite difficult. And in terms of the escape velocity, so yeah, there was a plot. Now I don't remember. It was in Darshan's paper in CACAD 2020, and if I remember correctly, yeah, it was a bit of a mix. But in most of the cases, probably was difficult for them to leave the galaxy. Although there are all these like many assumptions in this kind of velocity calculations, because it's constant velocity and so on. So, but it was a mix with mostly not able to leave the galaxy, if I remember correctly. But we can check later to confirm.
All right, there's another question there.
Hi, Chiara. A very interesting talk. I was wondering about the this plot specifically and the fact that you are interested also in checking the spatial distribution of the molecular gas in its sources. So I understand that your approach is to have large samples homogeneously selected to be sure of the trends that you're finding. Have you, however, have you considered maybe if there are some lensed sources that you could follow up with ALMA?
Well, no, no, not yet. There are some examples, however, at still a cosmic noon redshift 1, redshift 2 of lensed AGN. They were observed, I think, in CO 120-221 with the VLA, but it was very interesting in terms of spatial distribution because they could find that so similar to the cavity effect that was shown in the local universe, where they could see a depletion of CO. Let's say at the center of the galaxy. So I think that's a promising avenue. The problem is that for, you know, these non-lens galaxies takes quite a long time to integrate. So yeah,
also
is definitely
on this point, I know that it carries a lot of uncertainties, but have you also considered using C+ for the molecular gas mass? So it could help you with the integration time.
Yeah, it could help a lot, but the problem is that at redshift 2, well, it depends. It varies on a case-by-case basis, but it falls in the gap between bands for ALMA, so it's difficult to observe. But yes, something to consider definitely. The targets where it's possible. Yeah, thank you.
Okay. Is there any other question? Okay.
Thank you very much. Very, very interesting. A very deep dive into the quantitative work that you're doing. I'm wondering if I can ask you to stand back and look at the qualitative outcomes of what you're doing. Has your work led you to any conclusions about the origins, structure, or the evolution of the cosmos? It's a big question.
So, no, say it again, sorry.
I was wondering if you have any ideas about the bigger picture, that conclusions you can draw from the work you're doing in terms of the origins, structure, or the evolution of the cosmos.
Wow, that's a very, very broad and big picture question. Yeah, I mean, I think that especially for these studies of AGN outflows, well, AGN feedback in general, there is a lot of work, you know, on the outflows, trying to understand how they work on a small physical scale, like in the details. But we should try to get a step back and also look at different scales, also the medium, the circumgalactic medium, so all the gas that is surrounding the galaxy, because we have a lot of information there as well. Also in terms of bigger, let's say, spatial picture in terms of spatial scales, because it's not just I think it's clear from here that this kind of small scale effect on the galaxy, on the gas reservoir, on the dust, on the star formation rate are very difficult to constrain. But then if we take a step back and look at the gas reservoir as a whole, we could learn something very interesting about, you know, how the whole system of the galaxy, the ecosystem, if you want, is working. So I don't know if this kind of answers partially, at least partially, your question. Yeah.
Right. It's time for one more question. I don't see more questions, neither from remote. So thanks the speaker once again.
Thank you very much.
And now we have a scientific coffee in the cafeteria. And I would like to remind students to come here to check the attendance.